In the last lecture, we started with the graphs concept. We have discussed the concepts of graph and basic concepts of graph such as vertex, edge, what is meant by directed graph, what is meant by undirected graph. Again, in the directed and undirected graphs, there are two categories such as weighted graphs, weighted undirected graphs, weighted directed graphs, and how these particular graphs are going to be represented, and all these things we have seen. So previously we have seen the graph representations, graph representation. So in how many ways a graph can be represented using adjacency, adjacency matrix and adjacency list. You consider this diagram in which you have a graph. The graph is like this: the vertex 1, 2, 3, and 2 is connected with 4, 5, 3 is connected with 6 and 7, 4, 5, 6, 7 is connected with 8. This is the graph. Assume that we are going to discuss this graph. We are going to discuss the concepts in this lecture using this graph. Now, how you can represent using adjacency matrix? So for this, how many vertices are there? There are 8 vertices. So whenever you have 8 vertices, obviously you need to have a 8 by 8 matrix. Okay, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and you have 1. This is a row and column, right? 2, 3, 4, 5, 6, and 7, and 8. Well, so is there any one-to-one connectivity? Is there? There is no one-to-one connectivity, so it is 0. 1 to 2, is there any 1 to 2 connectivity? Is there? Obviously 1 to 2 connectivity is there, 1. Next 1 to 3 is connectivity is there. Remaining and all are zeros. That means there is no connectivity with the remaining vertices. So this simple adjustment that you can make it, right? So 2 to 4 to 5, 4 and 5, the connectivity is there. Okay, and also 2 1 connectivity is there. 1, okay, 1, 4, and 5. Next 3 to 1 and 6, 7 connectivity is there. In this way, 4, 5, and 6 and 7. 4, 5 is having the parent as 2, and 6 and 7 is having the parent as 3. And 4, 5 is having child as 8, and 6, 7 is also having child as 8. That means 4 to 2 there is a path, 4 to 8 is also a path. So you have to write for 4 at 2 there is a connectivity, and also at 8 there is a connectivity. For 5, connectivity is there with 2 and also with 8. For 6, the connectivity is with 3 because 3 is the parent of 6, and 6 is also having connectivity with 8. 7 is having connectivity with 3 because 7's parent is 3 and 7 children is 8. 8 is having connectivity with 4, 5, 6, 7. So 4, 5, 6, 7. This is the adjacency matrix. So now you fill up the places where it is empty here, because that means there is no path. So you fill up places 0, and here wherever the spaces are there, you fill up with 0. So this is the way you can build up the adjacency matrix. Now this adjacency matrix I am calling as graph. So now I want to see whether is there any connectivity between 1 and 5. So what I will do is graph of 1, 5. This is a two-dimensional array. That means graph of 1 means here 1 and 5. That is what we call 5 here. So the corresponding slot of 1 and 5 you are going to check. If it is 0, then if it is equal to 0, then there is no connectivity. No connectivity. Okay. In generic terms, I will mention it as row I and j. So graph of I and j. If graph of I and j is equal to 0, then it is no connectivity is there. Otherwise, there exists connectivity. That is, graph of I comma j is 1, then connectivity is available. For example, if it is a weighted graph, assume that the weight of this particular section is around 10. Okay, that means this particular edge weight is 10. Then from in order to represent in the adjacency matrix, what you used to do is instead of 1 or 0 as a boolean values, whether connection exists or not, you will place the weight value. That is from 1 to 2, instead of 1, I will place the weight value as 10. Right? That means in the weighted graphs, in the matrix that you form for that weighted graph, you will place the weight of the corresponding edge instead of the mentioning of the connectivity as a boolean value 1 or 0. Right? So this is the way the matrix representation will be done in the graph algorithms. So by this time you might have clear that how this particular matrix representation will be done in the graphs. While coming to the adjacency list, so usually adjacency list is a kind of a multi-list concept that we have studied in the beginning stages of this course. That means since you have so many zeros here than one, then it is better to convert this particular matrix into adjacency matrix, adjacency list, or we can say multi-list. That representation can be done via the particular linked list concept, which is called dynamic memory allocation. So for that, what you do is struct node. So representation of that is adjacency list representation, in which you will mention struct node star next. Okay. Then if there exists connectivity or not, that we are going to see. If there exists connectivity, automatically you will form a multi-list. But if it is a weighted graph, then what you do is int weight. Okay, int weight. That means that particular slot is occupied with the weight, and we should know what is the vertex number that is attached to this particular list. So for this, what I can do is I can write int vertex. So that means if it is a unweighted graph, okay, if it is unweighted graph, then this particular only int vertex will be available. If it is a weighted graph, you will be having only additional variable which is in the node structure, that is called weight. Okay, if it is weighted graph, that means this variable is to be used if it is a weighted graph. Since matrix operation is very easy for us and we can use it very fast, so that is the reason, even though it takes little bit memory, we are always preferring the graph representation for performing operations on graph. Okay, so what are the different operations that you can do on the graph? What are the operations? So far, by this time, you come to know what is in the tree concept. So, what are the different operations that are performed? Operations on trees. Operations on trees are said to be especially the traversal operations. Okay, and calculating the height, calculating the depth, calculating the breadth. Okay, like that you have many operations on graph. So like this, we have various other operations on graphs also. What are the operations on graphs? The first operation is a traversal operation. Okay, so traversal operation means how we will traverse this particular graph. In the same way, how we will traverse the trees. There exist three types of techniques for traversing the trees. One is in-order traversal, second one is pre-order traversal, third one is post-order traversal. Like that, you will be having the traversals in the graph. First traversal technique is depth first search traversal, which is also called as DFS in short. Next one is breadth first search traversal. In short, it is also called as BFS. So breadth first search and depth first search. Next other operation that we can do is the checking for the connected components. Checking for the connected components, that is uh, checking for articulation point, checking for pi connected components. These are the categories under the components. Next is spanning trees. In this spanning tree is DFS spanning tree and BFS spanning tree. Other operation is minimal spanning tree. We have seen trees are also called graphs, but trees will not be having any cycles, where in case of graphs may consist of cycles. But if you represent a full-fledged graph in terms of tree, then it is said to be a spanning tree. The spanning tree can be formed via DFS or via BFS. While coming to the minimal spanning tree, the minimal spanning tree is one that the tree that is constructed with the minimum number of edges. Okay, the tree that is constructed with the minimum number of edges, or the tree constructed with the minimum weight, if it is a weighted graph. Okay, tree constructed with a minimum weight or edges. Such trees are said to be minimal spanning trees. In order to identify the minimal spanning trees, we have two famous algorithms. One is Prim's. He is the author of this Prim's algorithm, and another is Kruskal's algorithm. These are the two popular algorithms that we can apply for identifying the minimal spanning tree. While coming to this minimal spanning tree, either you apply, that is minimal spanning tree obtained via applying Prim's algorithm is equal to Kruskal's algorithm. That means you won't find new minimal spanning tree. You will find the same spanning tree. Either you may use two algorithms for this. Either you, that is up to you. Choice is yours. Either you may use Prim's algorithm to identify, or Kruskal's algorithms to identify the minimal spanning tree. Now we will move on to the first operation in the graph, because for any of the remaining operations, we need to know the traversal operation, either via depth first search or via breadth first search. Any one of these traversal algorithms we are supposed to use to perform remaining other operations. Okay. The reason is unless until you won't traverse the graph in a particular manner, then you cannot achieve or you cannot visit the vertices or edges or traverse to the edges, and you cannot traverse to the entire graph. So the reason discussion of the graph traversal algorithms is very important. So first we will see the graph traversal algorithms. The graph traversal algorithm is, first one is depth first search, second one is breadth first search. So graph traversals. Let us see the breadth first search. In graph traversal, especially in the breadth first search traversal. The name itself indicating you that you are supposed to traverse via breadth of the graph. Breadth of the graph in the sense, you look at this graph. One, what is the breadth? This is the breadth. Okay, breadth means this horizontal. Then next horizontal, next horizontal. So recall the trees graph, the trees concept, in which one can be said as a parent, and two and three are the children of the parent one. Okay, three is the sibling of two because two and three are belongs to the same parent. Two is sibling of three, and three is also sibling of two. So in the breadth first search traversal, from the starting vertex, visit the siblings before visiting its children. For example, you started with one. Do one have any sibling? No. One itself is the starting vertex. Now, from one, you have to visit two and three because whenever you visit two, obviously two's sibling is three because two and three is having the common parent, right? Next, whenever you visit two, you have to visit four and you have to visit five. That means 2 is having the children's 4. Whenever you are visiting the children 4, obviously you have to visit its sibling also, that is 5. In the same way, once it is done, then obviously the rest of is 3 is left over. Whenever you have considered 3, you have to consider 6 and its sibling 7. Then only this particular breadth can be fulfilled. So first thing is 1 you are supposed to consider, next 2, 3, 4, 5, 6, 7, next finally 8. This is called breadth first search traversal. So in the breadth first search traversal, from the starting vertex, visit the siblings. Okay, visit the siblings before visiting its children. That is, before visiting the children of 2, visit the sibling first. Then, if all the siblings are over visiting, then you move forward to the visiting of its children. I hope by this time you clear what is meant by breadth first search. During this visit, how you know that if you consider this matrix, how you know that whether you have already visited that node or not? Because we have we have entries for two directional or bidirectional. That is, from 1 to 2 also the path exists, and also from 2 to 1 also path exists. If you consider this 1 to 2, obviously the path exists. And if you consider, since there exists 2, if you consider 2, again from to 1 already path exists. But from 1 to 2 only you have visited. You cannot revisit 2 to 1. So if you do like this, what will happen? It will fall into a loop because you are visiting 1 to 2, then you are going to 2. Again, you have identified 1 here, so you are taking the column value 1. Again, you are going to column row value 1. Again, from this you are going to 2. Again 2 to 1, 1 to 2, 2 to 1. Like that, you keep on moving on. So if you do like this, it will fall into an infinite loop. So we are supposed to avoid this infinite loop. For this, what we can do is, in the graph traversals, you keep a array. Array is required to keep track of the visit, to the mat to the vertex. So I will say it as visited. Okay, visited of I, where I is the vertex number. Okay, I is the vertex number. That means how many we need to initialize a visited array of size how much? Number of vertices. Okay. If the number of vertices are 8, then the size of visited is 8. Just like that. So whenever you visit one, whenever you visit one, and whenever you visit one, and you check for the connected vertices, then 1 to 2, 1 to 3. So whenever you visit one, you will initialize visit of one is equal to true. So initially, this visit of I or visit of visit array will be initialized to 0. Initialize a visited array of size vertex, okay, to 0. 0 in the sense it is false. That means you have not visited that particular vertex. If you might have visited a vertex, then it will be converted into true or 1. Since in C programming we don't have the Boolean operations like true and false, like in Java or in Python. So we are going to use the 1 and 0 to represent the visited or not. Now we are supposed to see the BFS. BFS is nothing but visiting siblings before visiting children. Before visiting children. From the starting vertex, you are supposed to traverse in such a way that visit the siblings before visiting the children. Recall the graph that we have drawn previously. In order to do this, first first vertex to be visited is first vertex is that is the starting vertex, that is 1. We are going to visit. What are its children? Since 1 don't have any sibling, obviously we are supposed to do the next thing, that is called visiting the children. What are the children of 1? Children of 1 are 2 and 3. How you will come to know 2 and 3 are the children of 1? That means you are supposed to go through the adjacency matrix. For 1, you have to check under which column you have the connectivity. So you have identified under 2 and 3 connectivity is there. That means 2 and 3 are the children of 1. Okay, 2 and 3 are the children of 1. How you can know that 2 and 3 is having the parent as 1? You go to 2, you find out the common parent, like common column where you have connectivity. That is 2 to 1, you have connectivity 1, and 3 to 1 also connectivity is there. That means same column name is there under which this connectivity exists. Thereby, you will be identifying that 2 and 3 is having the common parent as 1. So this is the way the programming has to be done. Okay. Now, since the first vertex is 1, so we are supposed to say visit of 1 is equal to 1, or we can say it is true. That means already we have visited 1. No need to visit again. So since vertex 1 does not have siblings, what we are supposed to do? Visit its children. So in order to do that, what we are supposed to do? What are the children of vertex 1? Children of vertex 1 are 2, 3, right? So 2 and 3 are the children of vertex 1. So in this 2 and 3, first 2 to be considered, next 3 to be considered. Okay. So since 2 and 3 are the siblings of children of 1, so 2 and 3 will be considered. But in order to hold these vertices in middle, we require a basic data structure. Otherwise, we cannot proceed further. So for this, I am going to take help of the elementary data structure called QEU. Q data structure helps in this traversal. That means what is the queue data structure here? The queue is first in, first out fashion, which is first in, first out fashion. The first visited vertex is 1, then it is having the children. Since the one don't have the sibling, we are supposed to visit its children. The children are 2 and 3. 2 and 3. Right? So since already vertex of 1 is visited, so we no need to visit again. So next element to be removed is 2. Whenever 2 is removed, already 2's sibling is already taken into consideration. So once you have taken the 2's sibling into consideration, so what we are supposed to do is we are supposed to make a visit of 2 as 1. So whenever you say visit of 2 is 1, then already 2 sibling is considered. The next thing to be considered is 2's children. What are the 2's children? Then vertex 2's children are 4 and 5. How you will identify? You will go to the adjacency matrix and you will say, is there any connectivity from 2? So after 1, because already 1 is visited, in the visited matrix we have seen visited, so we need to visit this again. So what to visit, since 4 is not visited and 5 is not visited, so 4 and 5 to be considered here. 4, 5 to be placed in the queue. Then once it is placed and visited of 2 is equal to 1, then we have to move the pointer, that is called the insertion will be done at rear and deletion will be done at front in case of queues. So front pointer will be incremented. Now it is coming to 3. Does 3 have siblings? Yes, 3 is having siblings, but it is already visited. So we cannot visit again. So that reason we have to visit only the children. So what are the children of 3? 3's children is 6 and 7. So 6 and 7 are the children of 3. Does 6 and 7 are already visited? No. 6 and 7 are not visited. So we are supposed to place 6, 7. And we have to make a visit of 3. Okay, we have to make a visit of 3 as 1. So once visit of 3 is 1, then the front pointer is incremented. Then we have 4. What is the 4 sibling? So 4 sibling is already in the queue. Once 4 sibling is already in the queue, the next thing is what you are supposed to do is we have to visit its children. What is the fourth vertex children? That is 8. So that means 8 should be placed in the queue. 8 to be placed in the queue. So whenever you place 8 in the queue, what will happen? The 4 is visited. Obviously, the 4 is visited. So here visit of 4 is 1. Then front pointer will be incremented. Now you consider 5. 5 already 5's sibling is visited because you have kept as a visit of 4 is equal to 1. So we need to do anything. And 5's children. 5 children is 8. 8 is already present in the queue. No need to visit again. So you make it a visit of 5 as 1 and you increment the front pointer. Whenever you increment the front pointer, then you are supposed to consider 6. Does the 6th sibling is considered? Yes, already 6 sibling is there in the queue. Only thing is you are supposed to visit the 6 children. 6 children is also there in the queue. So what you are supposed to do? You are supposed to make it as visit of here 5. Here it is 6. Visit of 6 as 1. Then visit of 6 as 1. Then you have to increment the front pointer. Then front pointer, that is 7. Now 7 sibling is already visited. it is already there in the queue. 7 children is already there in the queue. So again here visit of 7 is equal to 1. Okay. Then friend point will be incremented. 8. So 8 children. Okay, already 8 don't have any children, but it is having a bidirectional. That is, it is a undirected graph. So it will sometimes it may also check for 4, 5, 6, 7 as it is connected to the these vertices. That is 8 is connected to the 4, 5, 6, 7. It may check it because of our program. But already 4, 5, 6, 7 are visited. So we need to visit again. Now by this time, front pointer will exceed the rear pointer. Thereby the queue will become empty. As the front pointer is incrementing, you are going to display this on the screen. As we have seen this, whenever the front pointer exceeds the rear pointer, then we will feel that queue is empty and thereby will stop the operation. Thereby, you will get the queue values as 1, 2, 3, 4, 5, 6, 7, 8. This is the order of traversal whenever you go for breadth first search. So the breadth first search traversal is from the starting vertex visit siblings before visiting children. Like that, you have to go throughout the graph. In order to do this, we need a queue data structure to help us in traversal. The queue data structure we have seen how to use this queue data structure and printing the breadth first search traversal. Now we'll move on to the depth first search traversal. Depth first, we are supposed to go in deep. That means instead of visiting the siblings, we are supposed to visit the children first. This is what the difference. That means we are to visit the children. Children is at the deep. That is, once children is once children is 2 and 3. Now 2 children is 4 and 4 children is 8. Then you come upward. That means you are going deep and coming up. So how it is looking like? Whenever you go in deep and coming up, it is just like going down the tree and coming up. So whenever you go down the tree and come up, then you require a supporting data structure, what is called stack. So breadth first search require queue data structure to help the traversal, and depth first search require stack as the data structure to help the traversal. So from the starting vertex, visit children before visiting siblings. Okay, so it is quite opposite to the BFS. In BFS, you will visit the siblings first, then you will go for visiting of children. Where in case of depth first search, first you will visit the children before visiting the siblings. Okay, this is what the thing called depth first search and breadth first search. In depth first search, stack data structure, stack DS helps in this traversal. So stack is last in, first out. So first vertex is as it is. The first vertex is 1. Since first vertex don't have first vertex is 1, so we are visiting the first vertex. So first vertex is having the children. So you are supposed to push this. Particular children in the stack. The first vertex inserted is 1, and its children are 2 and 3. So these are the children of the 1 that are inserted into the stack. Now the top pointer is at 3. So here it is top pointer. So whenever we have a top pointer 3, then what we can do is since the roll of 1 is over, we can get the 1 out, and we make visit of 1 to be placed as true, or visit of 1 is 1, and now visit of 3 is also equal to 1. Now when visit of 3 is 1, that means you are going to pop the top element, that is 3 will be popped, and you check for the 3's children. 3's children is 6 and 7. So how you will know it is 3 children is 6 and 7? You are supposed to look at in the corresponding row of 3, where corresponding column is giving you the connectivity. So already 1 is visited, so you cannot visit again. So only thing is you have to visit 6 and 7. So whenever 6 and 7 was there, then here 1 can be removed here. Only 2 and 3 was pushed into the stack. Now whenever 3 is there, 3 will be removed out and you will be having 6 and 7 to be pushed into the stack. 6 and 7 already 2 is available in the stack. Now the top pointer is here. So now you remove the top pointer. So visit of now already visit of 1 is equal to 1 and visit of 3 is equal to 1 and visit of 7 is equal to 1. Now once 7 is visited, then 7 children need to be considered. What is 7 children is 8. So 7 children is 8. The reason is in the 7th row, you are supposed to look at the corresponding connectivity, in which connectivity is there with 3 and also with 8. Already visit of 3 is 1. Visit of 3 is 1, so we cannot visit again. So we need to select the children, that is 8. So 8 to be placed on the top of the stack. So now 8, then 6, since 7 will be removed from the stack, 2. Now the top of the stack will be at 8. This is top point. Now here we need to pick out the 8. Visit of 8 is equal to 1. Now when the visit of 8 is equal to 1, so obviously we are supposed to place the children of 8. What are the children of 8? Children of 8 means just you make this up and down, this entire graph up and down. That means 8 will be on the top and 4, 5, 6, 7 are the children of 8. In this 4, 5, 6 and 7, already we have gone through the 7 and we have also gone through the we have gone through the 7 and 7 is already visited. 6 is anyhow it is there in the stack. So only leftovers are 4 and 5. So children of 8 are 4 and 5 that need to be inserted into the stack. So 4 and 5. First insert the 4, then insert 5. Anyhow in the stack we have 6 and 2. Now 5 is at the top of the stack. 5 is at the top of the stack. So now we are supposed to pick out the 5. Visit of 5 is equal to 1. Whenever we pick the 5 out, then 5 children, that is 2 is the 5 children. Okay, 5 children is 2. And while coming for the down, that is 5 children is 8. 8 is already visited. So we cannot visit again. So only thing to be visited is 2. But 2 is already in the stack. So 2 is already in the stack. So we cannot visit again. That means 2 is already in the stack, so we cannot visit again. So nothing to be inserted in the stack. So once 5 has no role to insert some more elements, so remove 5 from the stack. Then whenever 5 is removed from the stack, we have 4, 6, 2. So no element to, no child to be inserted. Hence remove 5 from stack. So the leftover is 4, 6, 2. So 4 is having 4 is at the top pointer, or top pointer is at element 4. So when top pointer is at element 4, so we need to look for the 4 children to be inserted. So 4 children is 2 and 8. So 2 and 8 are already visited because 8 is already visited and came that 8 is removed from the stack also. and 2 is already existing in the stack. So hence, so this 4 can also be removed. So no element to be inserted in the stack. So what to be done is here we are supposed to make a visit of 4 as 1 and no children to be inserted, hence remove 4. So leftover is 6 and 2. So 6 and 2 are the leftovers in the stack. So 6 is at the top of the stack. So you look for the 6 children. Who are the 6 children? 6 children are 8 and 3. Anyhow, 3 is already visited. 8 is also visited. So nothing to be printed out. So that is the reason visit of 6 is true. Visit of 6 is true. And since there is no child to be inserted, hence remove 6 from stack. Then leftover is 2 in the stack. Leftover is 2. So top pointer is at 2. Try to insert the 2 children. Already 4 and 5 is also inserted into the stack. So hence we cannot insert further things, and already 4 and 5 is also visited. So nothing to be inserted into the stack. So visit of 2 is equal to 1. So visit of 2 is equal to 1 and no children to be inserted, hence remove from stack. Now what is the order of removal here? First we have removed 1. We have inserted 1 and taken out. 1 was taken out. And next we have removed is 3. 1, 3, 7, 8, 5, 4. That is the order of traversal is 1, 3, 7, 8, 4, 6, 2, 6, 2. Here 1, 3, 7, 8, 5, 4, 6, 2. 5, 4, 6 and 2. The total how many elements? 1, 2, 3, 4, 5, 6, 7, 8. So all nodes are visited. So this is the order of visiting whenever you go for depth first search. So DFS traversal will give you the value 1, 3, 7, 8, 5, 4, 6, 2. Once we'll cross check. So first 1 to be taken out. So 1. Then 3 to be taken out. Next one is 3. So 3. Next to be removed is 7. So 7. Next to be removed is 8. So 8. 8 will be removed. Next, once 8 is removed, we are supposed to place it by 4, 5. And next is 4, 5 to be removed. Next, once the 5 is removed, then 4 to be removed. Then 6 to be removed. Then 2 to be removed. After 2, the stack is empty. The operation will be stopped. So the depth first traversal will look like this: 1, 3, 7, 8, 5, 4, 6, 2. This is what the DFS traversal. So graph traversal is a basic step that you are supposed to perform for any operation on the graph. So for that we have discussed the breadth first search and depth first search. In the breadth first search, from starting vertex, visit the siblings before visiting the children. For this we are going to take the help of Q data structure. And in the depth first search, from the starting vertex, visit the children before visiting the siblings. For this we have taken the stack data structure. And the order of traversal of the vertices in the BFS will be differed with the DFS. So the traversal, that what are the values you will get in BFS is not equal to the values that you will get in the DFS. The traversal order will completely differ in both cases. This is regarding the graph traversal techniques that are breadth first search and depth first search. We will meet with some more concepts in the next lecture.